series off. We really do feel it's important to go back to basics. And so that's what this seminar series is all about over the coming year. And we're starting, obviously, our first series with a very basic question. What is a mechanical seal and how does it seal? And so without further ado, let me get started. And probably the first question we need to ask is, well, why choose a mechanical seal? And I think this cartoon graphic captures it well. Packing leaks, so mechanical seals are your choice for a leak-free operation. And hopefully you all understand a little bit of the humor into that, but that's what we want to focus on. So what are we going to cover today? As I said, this is the first module of the 2025 Mechanical Seal webinar series. And we really want to focus on some key points. First, what is a mechanical seal? It may be a very, very basic question, but I think it's one that we need to spend a few moments really understanding. And so we're talking all from the same page. Secondly, how does a mechanical seal seal? Third, what does sealed really mean? 4, what is the primary sealing interface and how does it function? How does it work? How does it operate? As well as what are the secondary sealing interfaces in a mechanical seal and how do they function? And then to bring that all together is, what are the leak paths in a mechanical seal and how does a seal really fail? And this series is, as I said, very basic. So we're not going to make you design engineers. You may see an equation or two, I think there's only one, but it's really to give you a basic understanding and grasp. So look forward to any questions you may have, and let's get started. So first of all, I think it's pretty obvious the need to move fluid is something that's been around and challenging man for decades, millennia. The first pumps were recognized back about 200 BC, the Archimedes screw, as we see here. But actually, the first centrifugal pump as we know it today was patented back in the 1800s, 1851. Prior to that, positive displacement pumps was the technology, as it still is today. But centrifugal pumps represent about 75% of all pumping applications around the world. So that's where we put a lot of focus and emphasis. But seals, the need for sealing is prevalent both in centrifugal pumps, positive displacement pumps, and other rotating pieces of equipment. So we want to, make sure we understand that seal's a seal. It's doing its fundamental job, whether it's in a pump, a compressor, a mixer agitator. Therefore, because there's pumps, there's a need for seals. So I'm going to start off with a question. How long should a mechanical seal operate in an application? And that's an important question to ask because a lot of people will give you very different answers. But that's the essence of what we're trying to drive with this educational series. And the answer to that, it depends on many factors, and that's what we're going to talk about. So here's an example. How long should a mechanical seal operate in an application? This is a real-life application. This was, believe it or not, a prototype 221 split seal that actually ran 23 continuous years without any maintenance interventions, without leakage, and it was taken out of service 23 years later, not because the seal had failed. They were refurbishing the pump, and the operator felt we probably should get replacement seal faces, a spare parts kit for the seal, and contacted Chesterton to do that. And it was a pretty astounding example, but it does show you what this technology can do if it's handled properly. And the reality is, as we go through, a lot of these applications aren't being handled properly, and that's why we see much shorter lives. But I like using this slide to introduce mechanical seal technology because seals can last a good long time if they're in the right operating environments. So we're going to talk about first principles, and I really like this quote. The most dangerous phrase in the language is "we've always done it that way" or "always done it this way." I've heard that throughout my career, And it's a really dangerous statement because it very much limits what you can do and how you can progress. So first key point, mechanical seals do not operate in isolation. They are part of a pumping system, and things that impact the pumping system will impact the mechanical seal. You need to keep that in mind. Number two, most seal failures are not related to the mechanical seal itself, but to the system issues. And, seal failure really is an indication of a bigger problem. And we're going to talk more about failure very briefly at the end of this. But when we say failure, the fundamental failure mechanism of a mechanical seal is it leaks. And we'll talk more about that in a moment. And third, and this is very important for all of us to remember, is never to try to solve a sealing issue by just changing the mechanical seal. The reality is, and the more you understand mechanical seals and how they function and why they function, you'll start to understand the clarity of this statement. If a mechanical seal is failing, there's reasons why, and just putting a new mechanical seal in its place is not a prescription for success, because probably the things that have caused failure before will continue to cause failure moving forward, unless you address it in your whole applications approach with the specific application you're dealing with. So hopefully that makes sense to everybody. So another question for y'all. How many seals are there in a typical pump? And it's interesting when you ask this question because you get many different answers. The reality is there's a lot. And you can see that, depending on the size of the pump, the type of the pump, this is a simple in-suction centrifugal process pump. And there's 1, 2, 3, 4, 5, 6, 7 different seals associated with that pump. Today, we're going to talk about the mechanical seal, which is what would be considered the main seal to the shaft. But the reality is any one of those seals can fail and cause excessive leakage. And you need to recognize that too, because many times a mechanical seal is blamed when it's not even the issue. Just from context, the mechanical seal technology we're dealing with today is about 100 years old. This is the first US patent that was filed on a mechanical seal. So the technology is fairly new. You think about pumps, again, they were patented back in the mid 1800s. And up until the advent of a mechanical seal, predominantly pumps were sealed with compression packing. And, there's limitations with packing. Packing is still a good sealing device technology. It has its place in the world, but it doesn't do everything or handle the same process conditions that a mechanical seal can. Also, we need to recognize that there's fundamentally 3 major categories of mechanical seals. And it's really based on the equipment that's being sealed. So the first category are, in essence, pump seals. And these are the seals that are, not only pumps, but turbines like hydroelectric turbines, fans, vacuum pumps would all fall under that category. The next category is mixers, agitators, those types of devices used for stirring, agitation. And then the third are process gas compressors. And from a Chesterton perspective, we design mechanical seals for pumps, mixers, and agitators. We do not design seals for process gas compressors. That is a market segment that Chesterton made a strategic decision not to enter into many years ago. And there are some very strong competitors in that arena today, and it just wouldn't make sense. And the reality is there's a lot more opportunities for you all in selling mechanical seals to pumps and mixers and agitators. So that's what we're talking about from a Chesterton perspective when we're talking mechanical seals. So another question for you to ponder. Are all mechanical seals alike? And again, when I ask this question in live audiences, I get many different answers. And the reality is, first, yes, all mechanical seals do operate with the same physical principles, and they share the same 4 basic components. And we'll get into those details in another webinars, one of the webinars coming up. but we'll review those very quickly for clarity. But there's also a note to this answer, and that is the designs and configurations are different. And it's those differences that offer pump operators, significant differences in operating capabilities and reliability. And that's the advantage we have, is to really pinpoint and show the customer the differences and show them, I use the term, a compelling difference. Why is our mechanical seal design different? Why is it better for them? And then being able to articulate that and really instruct your customer will tell you and help you to make that sale. So yeah, they're the same, but they're not all the same when you look at the nuts and bolts of what they do and how they are functioning. So as I alluded to earlier, there are many different types of configuration of mechanical seals. Just from a little bit of clarity, we have what are known as component seals. These are seals that are separate components that get mounted to the pump or the agitator mixer separately and then brought together. You have cartridge seals, and obviously I haven't shown split seals or gas seals. But what I'm trying to highlight here is if you look at the internal cross sections, they're fundamentally all the same. A mechanical seal is a device that you have a face that is rotating against a stationary face, and that's creating that mechanical seal. So what are the principles of operation? The purpose of a mechanical seal, and this is a very important point, is to minimize leakage of a fluid through a clearance between a rotating shaft and a fluid container. And many, many times I've seen people get confused and in trouble because they will say, well, my mechanical seal is leak-free. And the reality is, and I'm going to show you why in a moment, all mechanical seals leak. They have to leak in order to function properly. But taking a stand back, all sealing devices actually leak. We have data that proves that. Whether it's a gasket, an O-ring, a mechanical seal, a lip seal, they all leak a minute amount of fluid when operating properly. They have to or they will not work. So just be careful whenever you tell your customers or say something about being leak-free. The reality is most of these applications are leak-free from a visible leakage standpoint, but there's still a very small amount of vapor that is probably coming across that interface, whether it's packing, lip seals, O-rings, gaskets, or a mechanical seal. I hope that makes sense to people and you start to understand that. So, what is a mechanical seal? Again, there's different configurations. There's these things called pusher seals, which are nothing more than a seal that the O-ring actually moves back and forth. And then there's non-pusher type seals, which means there's no dynamic elastomer. The bellows right here is what's causing the motion. So what we're talking about with mechanical seal technology today is what's known as in-face mechanical seals. And that's because the faces are actually biased together in an axial position. First, realize that, these are precision mechanical devices that control leakage on a rotating shaft. And the dynamic sealing is accomplished by the stationary seal ring, which is the blue face in the upper right graphic, is biased against the rotating seal face, which is the golden face. And that is where the actual sealing is occurring. And this is known as the primary sealing interface. The stationary seal ring is also sometimes called the primary sealing ring, and the rotary seal ring is also called the mating ring. So different manufacturers or different technical groups will refer to those two seal faces in that terminology. So just be aware of that. And there's also stationary sealing is accomplished with the secondary sealing components we'll talk about in a minute. And that's really focusing on the O-rings, gaskets, bellows. The really any sealing interface that's not associated with the primary sealing interface. We'll talk a little bit more about that. So this whole concept of an in-face mechanical seal, the faces are perpendicular to the axis of rotation. That's the real key. What that means is you have the shaft axis and the faces are at a 90-degree angle to that. So they're not sealing on the shaft, they're sealing 90 degrees off from the shaft. And the face contact in a mechanical seal actually occurs for two reasons. There's an axial mechanical force, which is the spring that biases the faces together to create a static seal. But then there's also hydraulic forces that are interacting on that seal face, or the seal faces. It's the fluid pressure. And both of those are causing the faces to be brought together. So if we look at the primary sealing interface, we have to recognize, first of all, that there's two types of sealing occurring. First, there's static sealing. So when the pump is not in operation, these seal faces have to be able to obviously contain the fluid in the pump in the stuffing box and not allow it to pour out all over the ground. And then there's obviously what we more think about mechanical seals is the dynamic sealing when the pump is in operation. And again, we're talking about leakage control, and this is achieved by maintaining a small parallel gap between those two seal faces. And to give you a better understanding of this, we look at this graphic, and in a static sealing position, there's no rotation yet. The two seal faces are being pushed together, held together by the spring. And what happens is once rotation starts, the faces will actually open up because a fluid wedge is actually developing in that interface. And what's happening is within that wedge, that fluid coming across those faces, there's a pressure drop that occurs as it comes across the face, but there's also a temperature increase. And at some point with most fluids, typically water-based aqueous fluids, at some point across that interface, that liquid actually will vaporize. We hit its vapor pressure point and it turns to a vapor. And so you get a very small amount of vapor coming out on the atmospheric side of those seal faces. That is a good running mechanical seal. Now, certain fluids will not vaporize. Good example is oils. Typically, you will not vaporize the oil coming across the face. And so you'll actually see a very, very small amount of oil, call it wicking or wetting on the seal faces. Again, customers may look at that, and I've actually experienced this where they say, oh, your seal's leaking. And it's like, well, all seals are leaking, but that's a normal amount of leakage for this type of application. And that's one of the things you need to be prepared to understand and help your customers understand. But for typical aqueous fluids, water-based chemicals, those types of things, you generally will not see leakage or physical moisture. You typically won't see vapor. You may see some crystallization, like salt crystals, forming on the atmospheric side of the faces. That's all normal through the sealing process. So looking at the sealing up interface itself, the fluid is always flowing between the faces, and it has to be there for two reasons. One is it's a cooling agent. This is a dynamic device. You have friction. And so as the rotating face is in contact with the mating face, it actually starts to generate heat, and that heat needs to be cooled or you can cause failure. So that's what the fluid's doing. It's also there acting as a lubricant because, again, friction's present. And so, like any two devices in interaction, there is an element of friction that lubricants are used to reduce. So the fluid has to be there. The amount of flow, the amount of leakage coming across the sealing interface can be calculated and is using very sophisticated computer programs today. But it actually is characterized by this equation. And again, you're not going to memorize this equation, but I want to use it for the point of the conversation for this leakage, because the equation defines the parameters that result in the leakage coming across the face. And the first big consideration is this H cubed term in the equation. That is the physical gap between the two seal faces. And obviously, the wider that gap, the greater the leak rate. And the fact that it's a cubic or a function raised to the third power means that any change in that gap will create an 8 times or 8x increase in seal leakage. So when you're dealing with seals in the field and the customer is, gives you a call and says, hey, my seal's starting to leak, that leakage is occurring because there's a very small change in that gap of that sealing interface. And that's just important to be aware of. And typically that gap in a water-based fluid, low viscosity, that operating gap is only about 0.3 to 0.5 microns, about a half a micron, very, very small. But it's not the only thing that drives the leakage. We also have the pressure differential. Obviously, if there's a higher pressure differential from the sealed fluid to the atmospheric or whatever the low pressure side of the seal is seeing, that's a driving force to increase leak rates as well. The third parameter is the fluid viscosity. Obviously, the heavier the fluid, the higher the viscosity. Think about a 5-weight motor oil versus a 40-weight. The more viscous the material is, that gap will grow because you get more hydrodynamic lift. And then the seal size also plays into the leak rate. So this is, how we can characterize the leak rate. But the point to take here is it's a very, very small gap between those seal faces. And very small changes can cause leakage to increase significantly. And so that's the point of this. And to prove to you that seals do leak, this is some actual testing. This happens to be part of API 682 testing, which we have done and do, looking at the fluid's propane. And the graph, the blue line is the actual operating pressure, in this test case, 250 PSI. The red line is the actual face temperature. And you can see the faces are running about 80, 85 degrees Fahrenheit. And the black squiggly lines at the bottom are the actual emissions coming across those seal faces, measured in ppm. So you can see that in this case, the seal was leaking approximately 20-25 parts per million of methane is the detection method equivalent. And so there is a very minute amount of leakage coming across those faces, something you cannot see, but it's there. So finalizing this concept of the seal leakage, what happens if you don't have leakage? And this is where the problems begin. If there's no fluid film between the seal faces, you'll get very high heat generation because of the frictional heating. You will also get very high wear because there's no lubrication. So the two seal face materials are actually digging into each other. You can actually end up with thermal fracture. The heat grows so much that the seal rings will start to glow red and can fracture from that thermal stress. And ultimately, you will end up with catastrophic failure because of the wear going on inside the seal faces. If they don't fracture, they're going to be worn severely, and that gap is no longer going to be, half a micron. It's going to be much larger, and you're going to have a huge gush coming through that mechanical seal. That's why it's so important that all mechanical seals must leak to operate reliably. Are there any questions as I've gone through this fairly quickly with everyone? I don't think there have been. Joe hasn't interrupted me. So if not, let's talk a few minutes about. Yet. Okay, thank you. Thanks, Joe. What is mechanical seal design philosophy then? And simply put, the science of mechanical seal design is extremely simple. And it's easy to say that because what are you trying to achieve? First, we're trying to keep the faces flat and parallel. This is going to reduce both the pressure and temperature distortions within the designed operating range. We have to take that into account. Secondly, we need to keep the faces together without heavy contact. We want to maintain that half a micron distance between those faces. But we have to realize that we have to allow for dynamic tracking. And what that means is the seal faces aren't just sitting there in space, one spinning around with the shaft and the other stationary in the gland. They're not just sitting there stationary. They're moving not only rotationally, but they're also moving axially, moving back and forth with, hydraulic transients coming through the flow of the pump and all sorts of different things. So we have to maintain that face, keep the faces together, but not too together and not too far apart. And then finally, we need to provide the correct operating environment, making sure there's sufficient fluid for cooling and lubrication. Sounds very simple. Obviously, it's not. So what's the reality of these seal faces in operation? And the reality is they never absolutely run flat and parallel. We know that. It's just the physics of how these things work. There's always a certain amount of distortion that's in these seal faces. And the designers have to take that into account. And a good seal design, in essence, designs for those distortions. So as the distortions occur, and they will, the faces will tend to run as near flat and parallel as possible. So, there's lots of sources of distortions. First of all, there's thermal distortions. A lot of our processes are very hot. So you've got thermal loading there. Because of the dynamic nature of the seal, there is a temperature buildup within the sealing interface. So that all causes differences in thermal growth, which causes bending or coning. You'll hear the term used. Next, there's pressure stresses, hydraulic forces acting against these faces. They're tending to cause bending, pushing the faces down because of the hydraulic forces. There's also dynamic stresses coming from the motion and rotational forces of the pump operating. There's vibration. We're talking about the speed of the pump, the centrifugal forces that all are impacting these seal faces. And finally, mechanical stresses, or what I call static forces, from external to the pump, like misalignment between the pump and the coupling, pipe strain, misinstallation, the pump and motor aren't aligned properly, or the seal is misinstalled, so it's not aligned properly to the shaft itself. These are all the different stresses that occur that could create this distortion. And so what the designers need to do is think about the forces acting on the seal faces and designing to deal with them. So, from a hydraulic standpoint, what are the realities we're talking about? Well, pressure or vacuum. One of the big ones that's not given a lot of thought is this concept of a fluid shock or water hammer. Data has shown that, when a valve is closed too quickly, you can get a shock wave that goes through the entire pumping system and will end up in the pump stuffing box, hammering the mechanical seal. And that water hammer can be upwards of 30 times the sealed pressure. So think about that. So if you're operating a seal at 100 PSI and it sees a 30 times pressure wave increase for a very short period of time, that seal's now seeing 3000 PSI. And it's a very short, it's less than a second, but it's there, it's that hammer, and that can cause damage. Secondly, as I said, the dynamics, the speed, the vibration, the motion, all play into this. The mechanical forces, the pump motor misalignment, pipe strains. Pipe strain is something a lot of plants don't really think about or really understand. But you can cause a lot of strain and stress in the pump and seal from just the pipes hanging off the flanges and not being restrained properly. You can actually physically twist the pump housing. If you think about, an in-suction centrifugal sitting there, you could visualize the entire pump housing, the casing is twisting under these loads. That loading will transfer into your mechanical seal. And then finally, thermal. Again, excessive heat, excessive cold. You know, if you're dealing with cryogenic fluids, they can be very cold, and the same impacts of stressing can occur. So that's what's going on with these seal faces, and that's what has to be taken into account. And that's how designers look at these things to try to make sure we maintain that very small parallel gap between the faces in the primary sealing interface. Talking about secondary seals, you know, they provide sealing in the interfaces other than the primary sealing interface. So here's where we're talking about, you know, the O-rings, the gaskets in the gland. Those are all sealing interfaces. They may not be dynamic, but they are a sealing interface, and they're important. And all mechanical seals have them. And again, these secondary seals are doing two jobs. Some are being static, they're not moving at all, relative to any other surface. For example, the shaft O-ring on a mechanical seal is a static seal. You know, it's moving with the shaft rotation, but it's not moving in relationship to the shaft. On the other hand, this O-ring sitting here on the dynamic face that's spring-loaded, that will see movement back and forth as the faces are dynamically tracking. So that is a dynamic sealing interface. And then obviously the gland gaskets and such are static as well. And there are multiple types of secondary seals you'll find depending on the seal design. And just, you know, to show you a few of these, you know, obviously we just talked about O-rings and gaskets. But you can also have wedges. This is typically a PTFE or a Teflon wedge. The wedge is actually sealing against the shaft as well as sealing the rotating face to prevent leakage from coming through those two areas. But then you'll also have O-rings and gaskets as well. There's also what's known as elastomeric boots. And, you know, these are typically a polymer-based material. And again, the polymer selected is going to be dependent on the fluid that's being sealed, as well as the temperatures of the fluid. Generally, these are EPDM or FKM type materials. But again, you have the elastomeric boot on the dynamic rotary face, but you still have other secondary seals required, you know, again, gland gaskets, O-rings on the stationary faces. And then the final one is metal bellows. And this is a very specifically designed secondary sealing element that has multiple roles, because it's not only creating a seal, but it's also the spring that's biasing the faces together. These bellows are typically made out of materials such as Hastelloy C, alloy C276, or Inconel. Early bellows designs did utilize 316 stainless, but that's not as robust. And so in today's quality seals, you will not see 316 bellows. And again, as I said, that bellows has two functions. One, it's a secondary seal. It eliminates elastomeric seals in that dynamic interface, but it's also the spring load that loads the faces together, but still functionally the same as what we're seeing in any of the seals we're talking about. So when we look at the second, you know, look at mechanical seal cross sections, you know, here's the O-rings. You know, a single seal, you'll have a minimum of 3, maybe more. In a double seal, you know, you can see 1, 2, 3, 4, 5, 6, 7 at a minimum, or more, depending on the seal design. You do have the gland gaskets as well. So there's lots of secondary sealing interfaces in these mechanical seals. And again, there are dynamic sliding O-rings that we need to consider, whether it's an O-ring or a wedge or an elastomeric bellows, or the metal bellows, as I showed you. And the arrow, the yellow arrows show you where those dynamic elastomers sit. And think about this, that elastomer has to move freely enough or allow the face to track and move underneath it freely enough to keep the faces together. Because if there's anything that interrupts, say the O-ring grabs the face, it will prevent or slow down that motion, that dynamic tracking, and you'll get a momentary opening of that gap. And so you'll get more leakage. So many times a seal will start to leak purely because an O-ring has hung up, is a term you'll hear. The real technical term for this is O-ring hysteresis. And it's not allowing the seal faces to track back and forth together. So that's what the secondary seals are doing within the mechanical seal itself. So are there any other questions around secondary sealing before I talk about seal leakage at all? Okay, well then let's conclude with, when we talk about seal leakage, what are we really talking about here? So I want to ask the group a question, what defines seal failure? And I'm sure any of you that have been in the field for any length of time, you've seen this type of application before. And the reality is excessive leakage. Very simple, straightforward. If a seal's working well, you're not seeing a lot of excessive leakage. But what defines excessive? And the reality is the end user, the owner of the pump, the owner of the seal. They define what's excessive. So then the other consideration is, where's the leakage really coming from in that sealing application? And that's the challenge, because knowing where the leakage is coming from starts to answer the question, how do you correct it? How do you fix it? So, I used this term earlier, sealing devices are the leading indicator of pump failure. This is some data that's been around for quite a long time now. It was published, and it's been published a couple times in Pumping Systems magazine. And it's based on a survey that was done back in the 1990s, actually. And the survey focused on what's the typical reason for pump failure, and it's seal leakage. And, we do a lot of customer seminars, and you get a lot of pump users sitting in the room, and you ask them a question, what's the leading cause of your pump failures? And I can bet even odds they all will say seal leakage. And the reality is about 70% of pump failure is indicated by the seal starting to leak. There are other failures, other reasons, but seals tend to be the #1 leading indicator. But, and this is the real important but, the data shows that the seal is not the reason for most failures. It's the indicator that something else is wrong. And some of you have probably seen this data. This is from a study that was published back in 2011. And it's a really good study of pump and seal failure because it looked at over 11,000 seal failures across 143 different process plants. And very detailed seal failure analysis work was done. And the findings were, quite frankly, 50% of all seal failures, seal leakage, occurred because of system operation or process conditions. 22% were attributed to the sealing system, and we'll talk about that in a moment. Another 26%, when you look at both of these, is the bearings and maintenance and installation. But only 4% of the seal failures actually was a result of the mechanical seal itself. Something inside the seal breaking, a spring, a face, an O-ring. So this is really important to understand because, this is where I go back to the statement that if you're dealing with a customer that has a mechanical seal failure and they want you to fix it, don't start with just throwing another mechanical seal at it, because it's probably one of these issues up here that caused that first mechanical seal to fail. And if you just, off the cuff put a different seal in, it's like changing the parts on your car, right? You need to understand what's failed and what caused it to fail to put the right seal back in place. So the other thing to think about is, seals, we're talking about a sealing system here. It's not just the mechanical seal. And, it's important to take a systems approach. It's not just the component, it's part of the system. In some of the issues with failure, was the right seal selected for the application in the first place? I've seen many application failures because the customer didn't want to spend the money on the right seal for the application, or the seal supplier didn't want to sell the right seal for the application. And so that's one of the first questions to ask when you see a seal leaking. Is it the right seal for the application? Another big issue we see is there's no seal support system, and we'll talk about seal support systems in another one of these modules later on this year. But what we're talking about is, whether you have if it's a single seal, if you have a flush line or discharge recirculation line, or a double seal, you have one of these more elaborate barrier fluid or buffer fluid tanks. I've seen many customers who, because of the maintenance of the barrier fluid systems needed for double seals, neglect them, and then the double seal fails. Or is the wrong seal support system set up for the application? We see this a lot of times. And then a lack of routine maintenance. If you have a barrier fluid system, is it the right pressure? Are the barrier fluid levels still where they need to be? Because over time, remember, the seal is always leaking. So you lose both pressure and fluid level. That is why these tanks, these seal support systems have to be maintained. But it's not only for double seals, for single seals. How many times you go out in the plant and you find a flush line going to, whether it's packing or mechanical seal, and it's clogged. So in essence, it's starving the mechanical seal. These are all the different things that are happening to cause the seal to fail and start to leak. And then ultimately, we find a lot of times this whole system's just disconnected because it's too much maintenance. So things to be aware of when you're out in the field dealing with these mechanical seals. So, when we look at that data, what does the numbers tell us? Well, like I said, operating characteristics of the system are the leading cause of failures. And what are those? The pump's operating well off its best efficiency point. It's fluctuating all over the curve, different terms you'll hear. Cavitation, recirculation of the pumps, process upsets. Something goes wrong and, flow stops or flow pressures increase, flow increases, all sorts of things. That's the leading cause. Second leading cause are these mechanical issues, vibration, shaft deflection. We'll talk about that in one of the subsequent webinars in detail. Bearing failures, this misalignment, pipe strain considerations. And then finally, the seal support system, which is the third leading cause. And that gets back to what I just talked about. Wrong seal for the application, the wrong environmental control setup, lack of maintenance. So what are the leak paths in a mechanical seal? And as the graphics show here, in a single seal, whether it's, a cartridge seal is shown here or a component seal, there's actually 5 different leak paths because any one of the secondary seals can be a leak path as well as that primary sealing interface. In a double seal, depending on its design, you have up to 9, 10 leak paths. And remember, it's not only these sealing elements that can be the leak source, but also you can have a situation where either the gland itself has been attacked corrosively or by particulates that have worn through the gland, and you can actually get leakage coming through the gland itself. The seal is still sealing, but the actual pressure retaining metallic component is the cause of leakage. You need to be aware of that. So when you're out in the field and troubleshooting these things, look for where that leakage is coming from. So to try to wrap things up, what are the real requirements then for reliable operation of mechanical seals? First, you do need good equipment condition and operation. And I'm not talking pristine, but it needs to be good general practices. you need a proper seal selection and installation. You got to have the right seal for the application and the right installation, proper installation. Third, your environmental control and management program scheme needs to provide proper cooling, proper lubrication, sufficient pressure, sufficient flows, as well as excluding particulates and dirt that can cause interference with how the mechanical seal works. And then realize the environmental control can be provided from several different sources. We may use the pump fluid directly. We may modify that pumped fluid, or we may use an external fluid. And again, this is what's known as the seal support system. So really, in conclusion, mechanical seals are precision dynamic devices that must be treated properly to operate reliably. However, given the precision of these devices, they can be very robust and last and operate for a very long time. And that is if they're designed properly and applied and maintained correctly. So with that, that's the fundamentals of what mechanical seals are and how they function. How do they seal? Are there any questions whatsoever?